welcome everybody. Welcome to part 1, time series. So my name is Ioannis, and I work as a statistician in University of Edinburgh. So the first part is really just some simple time series models. So I will describe structural properties and time series models on ARMA models, autoregressive moving average, and I'll place some particular emphasis and focus on forecasting with ARMA models. So what is the motivation basically in time series analysis? So typically in all sorts of applications, or in our early days of statistical or data analysis, we postulate some toy models. So basically the starting assumption usually is that we do collect a sequence of random variables, let's say x1, x2, up to xn, and we typically assume that these can be, either independent or, in the simplest case, independent and identically distributed random variables. Of course, our favorite models here allow us to say that, we can put some probability distribution on these random variables and think of these are being drawn from some normal random variable with the mean and variance mu sigma squared respectively. So time series is really the study of observations that arise in some order and in particular time order. And therefore we can think that, our observations or our random variables are no longer independent. That's a standard assumption that's suddenly broken. And the key thing here is that there can be many ways of being dependent and independent. So almost all data are collected in some time sequence, some time order, and basically time series is a vast discipline that you can find it in a range of applications. So just to give you a flavor, they arise in climatology, for example, modeling temperatures, sea levels, or finance economics, prices, marketing, sales. I mean, the list is pretty much endless. It's really a highly important subject that requires us to understand it very well. So just some motivation. I mean, here we see a couple of first data sets just to start with. So these are standard data sets which are available in our statistical language in our software. So here we see the annual measurements of the level in feet of Lake Huron in the United States from 1875 to 1972. So the time series here is just plotted, the measurements are plotted over time, and we might start asking, are these measurements independent? In what sort of sequence do they arise? Well, surely we can start teasing out some features here. I mean, does the process have a constant mean? Does it fluctuate around a constant level, let's say? Well, it doesn't look like that. We can probably say that there is a sort of decreasing mean in the time series here. Maybe we can say a few bits and bobs about the variance. Potentially the variance might inflate over time. But these are just simple exploratory things we might just start thinking about. Here's another example that's basically finance, economy, growing markets. So these are daily closing prices of 4 major European stock indices. So we've got the German DAX, SMI, that's Switzerland. Here we've got the French FTSE, of course, UK's stock exchange. And it's sort of evident that there's a sort of increasing trend here with potentially oscillations here maybe being slightly different than at the beginning of the series. So another example here is CO2 concentration. Again, increasing trend. Of course, we see some additional characteristics here. We see annual cycles. So basically the series oscillates around a sort of increasing trend. If we were to think that we're filtering this trend out, we would sort of be able to say that, this December's CO2 measurement more or less resembles last year's CO2 measurement. So here there's a clear seasonality. So seasonality can be more complicated. So you can have sub-cycles, not just an annual cycle. You can have 6-month cycles. So here are airline passengers data from, these are totals basically in millions of passengers plotted against time being from 1949 to 1960. And here is the effect of technology effectively being into the series. So there is an increasing trend again in the number of passengers. Or we can look at the sort of time series. Here is just a last sort of data set, which is the number of sunspots. So sunspots are basically spots that appear in the sun. They do have a sort of 11-year cycle, and these are the monthly totals plotted over time. So again, we might just try and tease out some characteristics here. It's not clear that there is an evident trend, but of course there is a sort of distinct cycle appearing in the series. Right, that's just a motivation. So how do we basically analyze all these time series? How can we sort of start building probabilistic models that allow us to tease out these features automatically, or maybe infer properties about the evolution of the process, or ideally, can we say something about how these processes would look like, let's say, tomorrow? So I'm just going to describe a few things about, or go over, say, some time series basics. So what is a time series in a sort of formal mathematical sense? So it's basically a stochastic process. So it's a family of random variables, or a collection of random variables, x sub t, where t is well, ranges in a time set, calligraphic t. And that collection of random variables is defined on a probability space, pretty much meaning that we can allow dependence within our random variables. Okay, so with capital T, we do denote the random process effectively, whereas if we want to think about a realization of a time series, we denote it by a small letter xt, which is just thinking of drawing a sort of small omega out of the bag of the sample space. So typically in time series, the calligraphic set T, which denotes time, can take various forms. It can be just a real line, or it could be just a set of integers, positive, minus, or some sort of subset of the real line, let's say. But because of digitization, well, basically T, the time index, cannot contain any, say, sub-interval. Okay, so basically measurements are digitized. However, the time step with which we sample our series can be very small. So there are applications where delta t, let's say, can be just subdivisions of the second. Well, continuous time series basically can be thinned by subsampling at the points on a grid, or in some cases we might think that for continuous time series we might be able to obtain discrete time series by aggregating, say, the continuous time process over intervals. So a nice example here being rainfall accumulations. Of course, that's a continuous phenomenon, but we are never able to measure it instantly. So pretty much we aggregate over time periods. So for general discussion, we do take the set T to be the integers, and so basically our time series xt is recorded at time 0 or plus minus 1, plus minus 2, etc. Right, so just two main situations that the available data are part of a random sequence for which time t takes only integer values. Therefore, txt cannot be recorded at sort of, let's say, t equals a half or so. Or the available data are values of a random function, say xt, where t ranges throughout the whole real line. And that just gives you this sort of situation where I was describing before, where if we just imagine of, well, the scenario of measuring rainfall, let's say, Well, rainfall is a continuous phenomenon, so it's pretty much like a random function, but we do measure accumulations of rainfall in millimeters. Of course, if our phenomenon is a continuous time phenomenon, building stochastic models on discrete timescales might be dangerous, because basically, if we want to change the timescale, then our inferences might not just come over as nice from our originally constructed stochastic model. So if our phenomenon is continuous, we might just want to attack it, let's say, or think about building a continuous time phenomenon process. Sorry. Okay, measures of dependence. So we start always with xt, our time series, being a stochastic process, and then we can straight off define the say key ingredients we were describing before with the first few plots. So provided that the expected value of the time series at time t is finite, then we can define the mean or the expectation of the process to be denoted by Greek letter mu sub t, which is nothing more but the expected value of x at time t. And if mu t is non-constant, that means it varies over time, we sometimes call it the trend. Similarly, we can define the variance function. So if variance is finite for all time points, we can also define the autocovariance, which is basically describing the dependence within the time series. So at time t and time s, we might have two, say, random variables x, s, and xt. How are these related, basically? Okay, so a simple measure of dependence is the Pearson product moment correlation or covariance. So the Greek letter gamma here at st, so the autocovariance function is defined to be the covariance of xs with xt. So large values of this little guy here imply basically that on average the deviations of xs from its mean times the deviations of xt from its mean will be positive. And the other way around, if gamma is negative, well, these deviations will, the behavior of these deviations will swap around. So large positive values of gamma indicate that our time series is somehow strongly dependent on these two time points, whereas large negative values means that they are negatively dependent. So if xs is very large and the gamma positive, then it's highly likely xt will be large. Right. The key problem, though, with describing dependence purely with the autocovariance is that it's basically dependent on the unit of measurement. So instead, it's more appropriate to define the autocorrelation function, which effectively takes away this dependency on the unit of measurement by scaling with the product of the standard deviations. So some notes here. The covariance of xt with itself, so the covariance of the process with itself, is just the variance at time t, and that's gamma t comma t. And by Cauchy-Schwarz inequality, we can straight away see that correlation is bounded between -1 and 1. Some properties, the covariance function is semi-posi definite, meaning that for any, say, real constants alpha 1, alpha k, this sum here will always be positive. And the name we give to these functions is basically autocovariance and autocorrelation, which are just covariances and correlation, but we use the word auto to describe the dependency within the series. Right. Stationarity. So we started the discussion of time series just by saying, well, our standard toy model is just the IID random variables. Okay, so a way of start deviating from this assumption is just by injecting into the system this dependency or a covariance structure or a correlation structure. However, as we said, time series can be dependent in all sorts of different ways than time series that are independent. So a key notion of where we start extending our probabilistic models to more complicated scenarios, if you like, is the notion of stationarity, which in simple terms is, means that the statistical properties of the time series do not change over time, effectively. So if we denote by calligraphic S just any set, let's say, we can use the notation, say, U plus S, where U can be a scalar or a real value, to denote the sort of translated set, which is basically the set that consists of all the elements U plus S, such that S is within the set we picked. We can also use a nice notation to subscript our time series. So if we subscript our time series by a set, we basically mean the collection or the set of random variables exists such that S is in the set. S, calligraphic S. Okay, so coming back to just what we said, a strictly stationary process or time series is defined to be a time series where basically for any set we pick in the time index, so any sort of partition, any time points we pick from our time index t, and any sort of real value u for which, if we translate that set, the translated set will still remain in our time index t, then the joint distributions of x sub s and x sub s plus u are the same. So that really gives you this idea about a strictly stationary process being translation invariant in a distribution sense. Of course, that's quite a strong assumption. It implies effectively that the mean doesn't change, the variance doesn't change, and it also implies structure about the autocovariance and higher order moments. But in analysis and in real life applications, it's sometimes quite hard to check strict stationarity, and we can define a simpler notion of stationarity, which is a second order stationarity, or simply weakly stationary time series, which is defined to be the case where the mean doesn't change over time, and basically the covariance function gamma st does not really depend on the time points s and t. It just purely depends on how far apart these time points are. So purely depends on the absolute difference of t minus s. So just now focusing on our case where we sample on a discrete time index, and assuming the process is stationary, we can write our covariance function, let's say, at t, t plus h. Well, surely that does not depend on where exactly we are on the time index, so it doesn't depend on t, purely depends on the difference between t and t plus h. So in other words, that is equal to gamma 0h, or equally well to gamma 0, minus h, so it's symmetric around 0, which we can just define it to be gamma sub h. Okay, so the covariance function in cases of stationary processes is just a function of what is known as the lag between where we look our time series. Similar, we can do the same trick with the autocorrelation function and simplify it to a function of the lag. And just notice that both the autocovariance and the autocorrelation function are symmetric around 0. Right, so as we said, strict stationarity is quite hard to check in practice and to verify it. So well, it basically involves many computations. Whereas for second order stationarity, we only need to check whether the mean stays constant, the variance stays constant, and whether the autocovariance basically depends only on the lag. You can imagine that we can start extending these sort of definitions by, sort of third and higher order stationarity, where the skewness will not change, or the kurtosis will not change, etc. Okay, so the traditional sort of approach for time series modeling and analysis is that, we sort of tease out these characteristics we can see at our data, for example, trends or cycles. So we filter them out, and what we hope to is that what we are left with is nothing more but a stationary time series. Something that fluctuates around a constant mean level, and something that some sort of process whose objects, whose properties do not change over time. So in practice, we often pre-process the data, and that involves really removing trends, seasonal components, and other features. Right. So how can we start though building our probabilistic model? So how can we inject that covariance structure in our time series? Okay, so let's start with the simplest scenario, IID setting, also known as white noise. So a stochastic process is basically called a white noise if its elements are uncorrelated. And it's got a mean 0 and variance constant and equal to sigma squared. So the top time series plot shows you a realization from a Gaussian white noise, where the marginal distribution is also taken to be Gaussian. And of course, the scale here, well, I'm not showing you the scale there, but that's just a 0 mean. So 0 should be here, and you can imagine that, well, the scale here ranges from -3 to 3, just because the Gaussian distribution is taken to be a Gaussian with mean 0 and variance 1. The interesting bit here is the bottom plot, which if you zoom in, or if you compare it with the top plot, you might see some similarities. So there is some sort of movement between these two time series. So actually, if we just notice our white noise as it progresses, then we see a sort of dip here, and the same sort of dip happens there. Similarly, at that time point there and here. So actually, the way I constructed this bottom time series is just by filtering the white noise on the top. And by filtering the white noise at the top, really what I mean is that what I took is, I defined a new time series, let's say xt, which is the average of the most recent white noise events. So just quickly going back to these two plots, it might not be entirely evident, but well, these two time series are plotted on the same scale. And what we can see is that basically the variance of this bottom time series is well, smaller than the variance of the top time series. So actually, this operation of filtering here, or averaging white noise events, reduces the variance and actually induces correlation in the system. I mean, a sort of trivial exercise is to compute the autocorrelation function of the above moving average, as it's called, process, and also show that it's stationary. But we can just see the correlation being injected into that time series by looking at the sort of lag plots. So I've got 3 lag plots where I plot the process, the time series xt, with the lag process xt plus 1. And it's sort of evident here that you have a positive correlation, which somehow dissipates at lag 2 until it vanishes completely at lag 3. So actually, if you look at the time series, 3 lags apart, well, there is no overlap in the white noise events that could explain this correlation. So just by introducing this little nice operation here, we see that we can just start putting correlation up to any lag we want. Actually, if I were to average the sort of Q most recent events, I could have the same sort of story. I would have a correlation that dissipates with lag until it sort of cuts off after the lag Q. Okay. Random walk. So random walk is a very important time series and stochastic process in general, but it turns out it's non-stationary. So a random walk is defined to be, the time series is known to be a random walk if its dynamics are given by, just the value of where the time series was yesterday, plus a disturbance or innovation WT today. And just by plotting this time series over time, we'll see that it actually doesn't look like its statistical properties remain constant over time. Well, you can sort of see these local trends. So if you segment your time series here, you might observe local trends. But more importantly, what you can work out from this object here is that its variance is non-constant. So if we actually start from 0 almost surely, then we can think that x1 is going to be 0 plus a disturbance. So it's going to be just w1. Then moving forward, x2 is going to be x1. So just the innovation, just the disturbance, w1 plus w2. Eventually, solving this recurrence, you can write xt as just a sum of white noise events. So these are white noise events. So they are uncorrelated, or we might take them as independent. So in a random walk scenario, xt comes out to be just epsilon 1 plus epsilon 2 all the way to epsilon t. Okay, and a simple calculation about the variance of xt shows that that's going to be sigma squared plus sigma squared, which is t times sigma squared. Okay, therefore the variance does not remain constant over time, and it diffuses at root t. Okay, more interesting models. So we've seen the white noise. We've seen the operation of filtering the white noise, which injects a correlation. How about we think of the simplest case, let's say, of that of autoregression, where our time series xt is nothing more but a scale factor of what the time series was at the previous day. So it's alpha xt minus 1 for some values of alpha, plus a disturbance wt. Okay, well, let's have a look at that. How does it look like? Well, if alpha is taken to be positive 0.9, let's say, well, the present value is going to be more or less similar to yesterday's value. So it's going to be 0.9 yesterday's value plus a disturbance. So you see there's, again, some correlation in the system here. And just plotting the time series for the positive alpha case, you see the trace, you see the realization. So actually, it doesn't fluctuate as much as the white noise. Instead, it moves slowly. That's purely an effect of the autocorrelation. Whereas if you take alpha to be negative 0.9, then you have an oscillatory time series, which fluctuates quite a lot. OK. Right. So we're talking about autocorrelations and autocovariances, but how do we get them from our data? How do we estimate them? Well, really here, what we want to do is just obtain empirical analogs of the theoretical quantities of autocorrelation and autocovariance. So we can define the empirical covariance or autocovariance function for equally spaced data to be nothing more but the average, say, of these product moments here. Denoting by x bar the time series mean or average, really what we're doing here, we're looking at the deviations of the time series at time I, product with the lagged time series lag h, and we just take the average. So there is here the notion of correlogram, which allows us to plot, say, this function with respect to the lag. So the correlogram, or the autocorrelation function, is nothing more but the graph of, say, the empirical now autocorrelation function defined by the empirical covariance scaled by its variance. Remember, the variance is taken at lag 0. And that's just the graph plotted against lag h, where the lag h is just purely down to our judgment. So we can pick a sort of maximum lag over which we can plot the correlogram. Usually, n minus h minus 1 is replaced by n. So this minus n here comes from the degrees of freedom. It's a similar type of argument as with the sample variance. But often it's replaced by n, mainly because the estimator that has n here Of course, it's biased, but has better root mean square error. Right, okay, so here's a sort of very interesting theorem that we might just want to dig in. So imagine you've got a white noise, WT, and imagine that its fourth moment is finite. Of course, what's that fourth moment condition there? It might look funny, but you can sort of think that it's like the variance of the white noise is finite, so it doesn't have very heavy tails. And consider now a stationary linear process determined by, well, a sum, say, of all these white noise events, but weighted by some coefficient psi j. Okay, so that resembles this filtering operation we saw before, where we took the white noise and we filtered it by taking averages of the most recent white noise events. Though here, the difference being that we do allow, in our construction of our model xt, to put into future white noise events and past white noise events. So the sum here ranges from -infinity to infinity. Assuming a condition of this sort, together with a condition on the coefficient psi, for which we can construct a stationary time series, we have the following result. Basically, for such a process, for any fixed lag, the autocorrelation function will converge to a normal distribution with mean the true correlation and some variance that will shrink to 0. So basically, rho hat is a consistent estimator. And standard central limit theorem also holds in this case, which is nice. Of course, the computation of the variance here might be complicated because it will be dependent on the size. But what is interesting here is that if xt is white noise, meaning that the correlation will be 0, so white noise means all events are uncorrelated, all variables are correlated there. So correlation for lag h larger than 0 will tend to normal with mean 0, and variance scales as 1/n. So that's an interesting type of theorem here, because it could allow us to sort of build or construct hypothesis, statistical tests, let's say, for basically testing whether a white noise process is, for whether a time series process is white noise or not. How? Just by looking whether its autocorrelation estimates are significantly 0 or not. Right. So aside from the correlation, in time series analysis, we pair the autocorrelation function or the correlogram with what is known as a partial correlogram, which allows you really to remove the effect of intermediate values in the time series. So for x0, x all the way up to xh, imagine this being successive observations from a time series with some finite variance, and denote by x tilde naught and x tilde h the best linear combination of the intermediate values of x0 and xh, that is x1 all the way up to xh minus 1, that minimize the mean square error. That is the expected value of x0 minus x tilde x0 squared, and similarly for lag h. And to see that, I mean, you can imagine your time series being a Gaussian. Therefore, let's say if you have a time series which is driven by Gaussian white noise, or your time series being a Gaussian process, more generally, let's say, x0 all the way up to xh can be, well, imagine that being a multivariate normal distribution. So what is really the partial autocorrelation here? Well, if that's a multivariate normal, well, marginalizing over any variable will still imply that we end in a multivariate normal distribution. So for example, the x0 all the way up to xh minus 1 will also be a multivariate normal. And similarly, x1, xh will be a multivariate normal, just because a multivariate normal is closed under marginalization. So the best linear predictors, x tilde naught and x tilde h, are nothing more. But, well, if we were to write xh as a function of, xh apologies, x naught as a function of the remaining variables, well, we know the conditionals are normal, so there should be some coefficients beta 1 x1 plus all the way to beta h minus 1 xh minus 1 plus some noise term epsilon, which is Gaussian. Similarly for xh, there exists some coefficients gamma 1 x1 plus all the way to gamma h minus 1. So apologies. H minus 1 plus eta. So the partial correlation, the partial autocorrelation, is really the correlation between the disturbance terms in these two expressions. So the partial correlation here is the correlation of epsilon and eta. And intuitively, you can think about it as accounting for the effect of the intermediate variables. The nice thing is it's interpreted in sort of the same way as the autocorrelation function. And it's very useful in detecting Markovian structure in time series. So if your partial autocorrelation cuts off after a particular lag, that indicates that your time series can be thought of as a Markov process with the order up to that lag, for which the partial autocorrelation cuts off. Okay, so what is the effect of autocorrelation? So how does change inferential properties or statistical properties in the system? So I think the best way to describe this is through, a very simple case where we just start thinking about what is the variance of the average x bar, right? So in standard settings where our data are just IID from some distribution with, let's say, some mean mu and variance sigma squared. Of course, I'm not indicating any distribution here. I'm just leaving it blank. We do know that the variance of the average x bar is sigma squared over n. Okay? So we know that in the limit, as n grows large, the more data we collect into our analysis, our estimate is going to be, well, consistent, meaning it's going to converge with probability 1 to its true value. So how is this reflected, in the case where we no longer have IID settings, but we have a time series? Right. So so a simple calculation here can show that the variance of x bar, the sample average, well, so what would that be in the case where we would have autocorrelation or autocovariance in the system? So that's, let's write that down simply. So that's 1n minus 1, x1 all the way to xn, and that's n to the minus 2, the variance of the sum. Okay, but because we do have, because these random variables are no longer uncorrelated, when we are computing the variances of sums, we need to take into account the covariance structure. So you can imagine a sort of big matrix here, where on the diagonal you've got the variances of n of these. On the off diagonal, you have n minus 1 lag 1 covariances. Well, then n minus 2 lag 2 covariances, and so on. So that's going to be n minus 2, and we'll have, well, n times the variance, so that's going to be n sigma squared plus n minus 1, the autocovariance lag 1, plus n minus 2 autocovariance lag 2, all the way to the last bit here, which is autocovariance with lag n minus 1. So we've got gamma n minus 1 times 1. But we need to take into account also these guys over there, so there's a 2 coming out. So, yes, Chris?
I don't think you want a 2 there because you don't want it on the diagonal terms, only on the...
Yes, I mean, you're right. I mean, 2 only enters basically in these coefficients here. Thank you. Thanks. So a simplification of this formula leads to the first displayed equation, where you see now that the variance of x bar is just the variance divided by n. That's just something like sigma squared over n, similarly to the IID setting, times 1 plus, and now we've got a summation of these autocorrelation, say, coefficients at all the lags. So imagine now what would happen if the correlation was positive at all lags. So basically, this guy here would be positive, which would mean that the variance would be inflated, as opposed to the setting where things were completely uncorrelated. So injecting correlation in the system inflates the variance, say, of the sample average. And you can sort of think that this quantity here changes, in some sense, the amount of information that you have. So in IID settings, the amount of information you collect are just n data points. In a time series setting where you have, again, n data points, you cannot regard your information as being collected in a similar way or being equal to that of coming from n independent data points, but it has to be smaller than that. So positive autocorrelation amounts to there being fewer than n independent observations. Okay, so how do we test whether we have autocorrelation or whether a process is basically white noise? So that's very useful. That's a very standard and useful procedure in time series analysis, where we typically detrend our series, we remove all the cycles, and then in the end we might be left with a sort of residual process that we want to see. Does it still have an autocorrelation structure in there or not? So tests, statistical tests have been developed for this purpose. So, the sort of standard statistical test due to Box and Pearce, which was later improved by Young and Box, uses basically the fact that for a white noise process, the autocorrelations are 0, but they have to be 0 for any sort of lag. Okay, so the statistical test of Young and Box, denoted by Q sub m here, takes into account this property. So basically, it's defined to be a scaled version of the sum of, again, appropriately scaled squared autocorrelation coefficients. And it's not surprising that this comes out as to be a chi-squared with m degrees of freedom. I mean, in the limit, the correlation coefficient here, the empirical correlation, has a normal distribution. So when you square it, you end up having a chi-squared. And if you sum m of these appropriately scaled to account for the variance of this autocorrelation coefficient, you end up having a chi-squared with m degrees of freedom. However, you might start saying, well, what should m be? How many of these autocorrelation coefficients should I just put into that statistic? And you can start, well, of course, trying to do the test for several lags here, m. But the sensitivity of Q to different types of departure from the white noise will depend on m in various ways. But if you think that you take m very large, then it's highly likely that you reduce the sensitivity of that test because some of these estimates here will contribute no information about the lack of the fit. Whereas if you take m too small, you again might reduce sensitivity of that test statistic, just because your estimates here should contribute information about the lack of fit that are missing. So typically what you do is you plot the significance level, or the p-values, let's say, of qm for different m, and just see if it's too small for a range of values. Okay. So in our, there's a standard function in our box.test that comes with Bazar. So here, for example, for the Lake Huron, we saw right at the beginning, if you just type box.test, you give it a time series object, and you specify the type. You can also put the sort of old Box and Pearce here statistic. You'll get you'll get a p-value which is much less than 5%. So at the 95% confidence level, you reject the hypothesis that your time series basically comes from a white noise process. So there is some correlation in there. Okay, so another important test for time series is that of stationarity. So apart from just testing whether a time series is a white noise process or not, what is also interesting is it stationary? And the test I'm describing on this slide has its roots from econometrics. It's called the KPSS test from its authors, and really it relies on just postulating a particular model for your data. Okay, so the model takes the form that it's shown on the displayed equation. So xt here is just has a linear trend, xi times t is your time, plus now two stochastic processes, two time series here, one eta, the other one epsilon. So here eta is assumed to be a random walk, whereas epsilon is assumed to be a stationary time series. So the test here is constructed really by, well, testing whether the variance here of that disturbance or of that random walk is 0. In which case, if the variance of that disturbance W was 0, then eta wouldn't change at all. It would be always the same. Eta t will be equal to eta t minus 1, and so on and so forth. So really, it would contribute as a mean level in the formulation of a time series here. Of course, the test also allows you to assess whether the slope parameter xi here is 0 or not. And there are two types, the so-called level stationarity, where you test jointly whether the variance of the random walk is 0 and the slope is 0, in which case you recover that x is actually exactly stationary. And there is also the trend stationarity, where you just marginally test whether the variance of this random walk term is 0, in which case x minus its trend is stationary. There are some details on the slide about how the test is constructed. I'm not going to go into a lot of detail, but I mean it's useful to say that it leads to a sort of nasty asymptotic distribution, which comes out to be an integral of a squared Brownian bridge for the statistic defined in this equation. But again, these tests come with Bazar, no need for packages. It's called the KPSS test. And again, it's got an argument here that allows you to test whether it's trend stationary or level stationary. Here for the sunspots time series, the annual sunspots, you might just do the two tests separately. So the trend stationarity comes out with a p-value of 0.1, which is larger than 5%. Therefore, leading us with not sufficient evidence to reject the null hypothesis of the process being trend stationary. Whereas for the level stationarity here, the p-value is sort of marginally less than 5%, showing you some evidence for rejecting basically the null hypothesis of the sunspots being level stationary. And actually, you can sort of see that straight away from the time series plot. The sunspots sort of have an increasing trend over time. But just thinking overall here with these sort of results, at the end it might not be too problematic, let's say, to fit a stationary time series to these data. Maybe it's not going to be the best thing, but we can try and do that. Okay, so how do we remove trends? How do we remove cycles and all the like? So that's really a very simple approach to doing so. It's really differencing the time series. And to do so, we need to define what is known as the backshift operator. So the backshift operator B acts on stochastic processes. So B acts on xt and shifts it by one lag. So B times xt equals xt minus 1. It's really an operator that acts on time series. And you can think that the first difference of a time series xt, let's call it dxt, is equal to I minus b times xt. So just expanding the bracket here, I'm going to get xt minus bxt. Therefore, it's xt minus 1. And higher order differences are constructed in a similar way. So the second order difference here is just a difference of the differences. And it's really taking basically I minus b to the power 2, acting on the time series. So the nice thing about this operator is that it allows you to remove polynomial trends, basically. So if you imagine you had a linear trend, then a first order difference would basically filter it out. Actually, it's quite nice that if you have a time series, or if you have a sort of model where it's got a polynomial trend, so p here denotes a polynomial of order k, let's say, plus some noise, then it turns out that the kth order difference removes that trend. So it's a sort of high-pass filter in some extent that removes all the low-pass oscillations. So, for example, you can think first-order differencing in the random walk setting. That would lead to just the white noise, which is stationary. Or you can also think about removing cycles by taking, say, well, higher order differences here, but not in the sense we described before, but in the sense of, sorry, taking your time series xt and taking away, say, the time series lagged at minus k. The issue with differencing here is that although it's nice and intuitive to difference your series to remove the trends, it can result in complications. It actually complicates the dependent structure, or it can inflate or deflate the variance, and so on. So beware. So don't just feel like, ooh, I'm just going to take my nice favorite backshift operator and apply it on the time series, or take the first order differences and I'm fine. It needs more thought into, why should we really model or difference our time series. Right. So that's where we're leading to the end of the time series basics here. So I really want to stress on what is known as a causal process. So we saw again that idea of injecting correlation into the system by filtering the white noise, and we defined really the linear time series to be a linear combination of all the white noise events throughout the whole universe, let's say. So xt is a sum from j equals minus infinity to infinity of coefficients ij times white noise events lagged by j. Right, we saw some conditions on these coefficients here for that process to be stationary. And we somehow quickly mentioned that the difference between the example we had initially with the moving average is that, well, in this representation, we do allow future white noise events to influence the present value of the time series. Right, so a causal process really is a process where any psi for which it couples with a future white noise event is 0. So psi minus 1, psi minus 2, for which we will be getting wt plus 1, wt plus 2, is set to be 0. Therefore, there is direction flowing only, well, we only have a flow in one direction from the past to the future, okay, and not from the future to the past or the present. And that's quite important for forecasting, basically, because otherwise you wouldn't be able to do forecasting. Okay, so a causal process really truncates this sum. So by setting these psi's here of all the future events to be 0, but using the backshift operator, we can do right, say, the lagged white noise events by powers of the backshift acting on the white noise process. And eventually we can combine this into a very nice notation, very compact notation. So just by replacing our wt minus j by b to the power j wt, and defining the sort of operator psi b here to be equal to that expression down here, we can sort of compactify this notation into a much simpler one. Okay. So that's pretty much all I wanted to say about time series basics, and we'll move on to the sort of standard time series, standard linear time series, which are the ARMA processes, which are really combinations of moving averages and autoregressions. And nicely enough, we'll see that these also come up to be linear stationary time series. So everything we've said so far applies for these processes. So what is an ARMA process? Well, to understand the ARMA process, it's useful to split everything into its pieces. So it consists of an autoregression and a moving average. So let's see what's an autoregression. So definition here pretty much, we've got the autoregressive process, which is just the extension of the AR1 process we saw before. So an autoregressive process order P, shorthand is ARP, is of the form xt being a linear combination of its past P values plus a disturbance Wt. And we do assume that x is stationary here, and alpha 1 all the way to alpha p are constants, for which the last one, the pth one, is non-zero. That's basically needed to have order p, otherwise we'd reduce it to order p minus 1 if the pth was 0. And we can also extend that to a process that has non-zero mean. So I should stress here that the ARP process of this form has 0 mean, but you can replace it to an autoregressive process with non-zero mean by just replacing these x's here by x minus a constant level mu, which will happen to be the mean of the process. It's really like shifting the process by a constant level. So, employing or using again our favorite operator here, our backshift operator, we can rewrite this expression by having, well, let's see that. Well, xt minus 1 will be bxt, xt minus 2 will be b squared xt, all the way to b to the power pxt. And if I just take all these terms to the left-hand side and pull xt out, I will be left with my xt minus alpha 1 xt minus 1 minus alpha 2 xt minus 2, and so on. So the backshift operator can, allows us to also write the autoregressive process into a nice form, for which shorthand we write it as the autoregressive operator alpha b, given by this expression. And this also suggests that we could write our time series xt to be the reciprocal of this autoregressive operator times the white noise. And that is useful if we basically want to get the causal representation, which is nothing more but the linear combination of all the previous white noise events. Okay. Of course, to find psi, the standard trick is to expand this polynomial here, this reciprocal of the polynomial, into a sort of binomial series, or Taylor series, if you like, which allows you to get the coefficients of psi as the coefficients in the Taylor series representation. So similarly, we can have the moving average process of order q. So xt here is defined to be a linear combination of the past white noise events. So x equals a disturbance at time t plus a weighted combination of the q previous white noise events. And again, these thetas here, these coefficients are constants, for which theta q, the last one, is not 0, just to retain the order q. Similarly, things extend to in a straightforward manner as before. We can shift the process by a constant level. So if we want to have a process which is a moving average, but with mean mu, we replace xt with xt minus mu. Again, we can define the backshift. We can use the backshift operator to compactify this equation here. So again, we can write all these white noise events as, well, products of the powers of the backshift operator times the white noise at time t, in which case we can pull out the white noise at time t and retain this moving average operator. And unlike the autoregressive process, for which conditions are needed on the coefficients, this process is always stationary. It's just a combination of white noise events for any values of theta. And here's an exercise that asks to see basically that if you take two moving average time series, both order 1, okay? So imagine you have two time series now, MA1. One is with coefficient theta 1. The other one is with coefficient 1 over theta 1, theta 1 being the same guy there. The question asks you to show that the statistical properties basically are of these two time series are the same. Just to show that the MA1 processes with these two different parameters are statistically indistinguishable. So if we write down the dynamics of these time series, so we've got an MA1, 0 mean, let's say, so xt is going to be equal to the white noise Wt plus theta Wt minus 1. And it suffices to just compute, the covariance, the autocovariance of the time series at just two lags, at lag 0 and lag 1. So if we look at lag 0, so that's going to be the variance of xt. Okay, these are uncorrelated white noise events with variance sigma squared. So you have a sigma squared from here and a theta squared times sigma squared from there. So you're going to have, you can pull sigma squared out and lead to the variance of your MA1 process being sigma squared times 1 plus theta squared. Okay. How about the autocovariance, say, at lag 1? In a similar calculation, we can have gamma 1 here being the covariance of xt with xt minus 1. And let's just replace these two guys by their equivalent representation. So these are MA1 processes. So we have Wt plus theta Wt minus 1. And I've got a Wt minus 1 for the second bit plus theta Wt minus 2. Okay, so now we need to notice that these are white noise events. Therefore, t with t minus 1 is going to give me 0 covariance. T with t minus 2 is going to give me also 0 covariance. However, that's a term where it's going to influence the autocovariance, whereas this one is also going to give me a 0. So basically, if I were to write the covariance of these two variables explicitly, I would end up having the covariance of theta times Wt minus 1 with Wt minus 1. And I can take theta out, and I'll result with a covariance of the white noise with itself, which is theta sigma squared. Just by taking theta outside and having the covariance of Wt minus 1 with itself, which is a variance of the white noise sigma squared. Right, so we've got two objects here. We've got gamma naught, gamma 1. Let's see the correlation. So the autocorrelation at lag 1 is going to be the autocovariance at lag 1 scaled by the variance, gamma naught. So that's theta sigma squared over, and we had sigma squared here, 1 plus theta squared. Right? Okay, surely now, if we change from theta 1 to 1 over theta 1, let's say 1 dash for the second time series, that's just changing theta here to 1 over theta. So that's going to be 1 over theta divided by 1 plus 1 over theta squared. Right? And if you pull 1 over theta squared out, put it on the top, you'll see that that's exactly equal to theta 1 plus theta squared. So the two are exactly the same. Basically, if you get two MA1 time series, one with coefficient theta, the other one with 1 over theta, their autocorrelation functions are exactly the same. So that's a shame. So we need some sort of conditions to keep bits of, keep those we want and keep those we don't want, purely for identifiability reasons. So a moving average is called invertible. A moving average process is called invertible. if it has an infinite autoregressive representation. So that's just the dual representation of the linear time series. So remember before we saw that we can write a time series or a causal autoregressive process as an infinite linear combination of all the past noise events. Now what we're doing, we write the white noise as an infinite linear combination of all the past values of the series. So it's just the reverse calculation, really. And we call the moving average process to be invertible if it has this representation. And that's just needed to ensure identifiability so that we don't end up having two time series with the same correlation function but different coefficients theta. One, let's say, being theta, the other 1 over theta. Right. I mean, I'm going to leave that as a sort of exercise, the second bullet point here, to check that for this example, we just went on the board, which of these processes is invertible. But what I want to move on quickly now is the combination of these two models, of course. I mean, we didn't say much about where these models are useful so far. Where is an AR process useful? Where is an MA process useful? Okay, that purely depends on their structural characteristics. So an AR process has a specific autocorrelation and partial autocorrelation behavior. And similarly, the MA process also has a specific behavior for its autocorrelation and partial autocorrelation function. In some way, we can think that the autoregressive processes are quite useful processes because just they relate the present with the past. So they've got this diffusive behavior, whereas the white noise, the moving average processes really link your present value with combination of past white noise events. So, you know, the purposes of the models, your modeling purposes will dictate which one is best for your analysis. However, the combination of the two really, you know, gives you a sort of big grand model, if you like, with which you can play with and do data analysis. So the moving average process of order P and Q, shorthand ARMA P and Q, is just a combination of the two. So your present value is equal to a linear combination of the P previous values of the series plus a disturbance, term W, plus now a linear combination of past disturbances. Okay. Of course, the usual trick to shift the process by a constant level and get a mean mu, just replacing this representation xt by xt minus mu. And again, using our backshift operator, we can, you know, boil this equation down into a much more compact expression. So we do write AB times xt equal theta b wt, where A and theta here are being the autoregressive and moving average operator, respectively. Okay, so the properties of this process is intimately tied with the properties of these polynomials here, of these operators. Say alpha z and theta z, for which we might take z to be just a complex number. Let's define, say, d here to be the unit circle. So it's all the complex numbers for which their modulus is less than 1. That just denotes a unit disk in the complex plane. Okay, the first point we might want to make is that, you know, if these two operators here had common factors, then they would just knock each other from left and right hand side. So basically, we don't allow ARMA processes for which the autoregressive and moving average operators, you know, sharing the same factors. That's just called parameter redundancy, basically. So again, we can think about whether an ARMA process is causal. So, you know, just starting by the defining equation of the ARMA process, we define it to be a causal process if it can be written as an infinite linear combination of the past white noise events. So therefore, we get the sum of coefficients psi times previous white noise events, where the psi's here are absolutely convergent. That ensures causality. So there is only one direction from the past to the future. And actually, it's invertible if it has this dual representation now, where the white noise is written as an infinite linear combination of the past values of the series. So in the first case, x is written as a function of w, if you like. In the second one, w is written as a function of x. Okay, both cases require, causality and invertibility require absolute summability here of the coefficients of the series psi and pi. And we end up with the theorem. So an ARMA PQ process is basically causal if actually this autoregressive polynomial alpha of z cannot be 0 within the unit disk. And similarly, it's invertible if this if this moving average polynomial here cannot be 0 within the unit disk as well. Or in other words, if the roots of both a and theta lie outside the unit circle or outside the unit disk. So there is some fascinating and beautiful math, there are beautiful math behind why that's a story, but we're not going to, delve into too much detail about that. Of course, in practice, if you want to basically assess whether your time series, your ARMA time series is causal and invertible, you would have to check that by basically finding the roots of these two polynomials and checking whether they are outside the circle. But why ARMA processes, right? Why do we want to use these processes? Well, really, they're sort of combinations of two different models that share some dual properties, and they have some sort of intuitive, explanations. However, if you combine them, you might start thinking that we lose this intuitive explanation of, well, why will we want to use the ARMA process for modeling our time series, right? It's typically used as more of an empirical sort of model where our estimates of these coefficients, the autoregressive coefficients and the moving average coefficients, are nothing more but just summary statistics, but with no real implication about what's the scientific basis of the phenomenon under study. However, because it's a combination of two still flexible models, you can think of the ARMA processes or the ARMA models as being a quite flexible class of time series, purely because they do allow a wide range of behavior for their autocorrelation and partial autocorrelation functions. So, of course, increasing the orders here will give more flexibility at the cost of putting more parameters into your system, and it can provide effectively a wide range of different types of behavior. However, even with P and Q being of small order, they can still give you flexible time series models. Okay, so the most important aspect for these processes is that they're quite useful for forecasting, or for settings where the autocorrelation function is not just of primary interest. So just to recap, ARMA models will not tell you really why your data behave the way they do. They just don't serve as models for explaining the scientific basis of your phenomenon. It's really empirical models that allow you to tease out these properties for your time series, okay? Purely second-order properties, autocovariance and autocorrelation. Instead, if you split the ARMA into its building blocks, which is the AR and the MA, then you might have more interpretable models. For example, the autoregressive models, they do have Markov structure, right? Given if I'm at the present, well, given the knowledge of the present, past and future is independent. Or, for example, if I want to predict the future, I might only need just the two previous values, let's say, or the yesterday's value. So that's just Markovian structure, which you'll see in more detail in part 2. So actually, AR models are much more interpretable. Similarly with MA models, these stem from weighted averages of white noise events, and they could be interpretable as well. So just a quick illustration here. How do we fit ARMA models in R? So here are annual sunspots. We just go back to our initial example with the time series of sunspots. So there's a wealth of functions and packages in R for time series analysis. The base R comes with AR, or the function ARMA, or ARMA.sim. So AR fits AR models. ARMA can fit more complicated models like ARMA and integrated ARMA, which we're not going to cover. Whereas the ARMA.sim allows you to simulate from the models. And my favorite, which is the forecast package. So if you want to have a functionality for fitting MA processes, or if you want to have automatic model selection, then you can use AutoArima. So here, just a quick example, just fitting the model to the data just by using base R. So we're storing in AR.model the output of the function AR fitted to, say, the sunspot data. And we obtain, say, through automatic model selection, a 9th order autoregressive process. So basically, the AR model here, the fitted model, gives 9 coefficients. So the order of the AR is 9, and we can see the sort of estimated coefficients here. So the first coefficient, alpha 1, is positive, then becomes negative and negative, then positive, negative, and then starts somehow alternating. So if you look at your time series more closely, you might just start and ask, how does the correlation look like? Well, basically, if you look your time series at, say, 9 to 12 years apart, it's more or less the same. However, if you look at it over 5 years' time, lag 5, you'll see that it's quite different. So basically, there is both positive and negative correlation in the system there, and hence the reason for having to have all these coefficients there, just to mimic the properties of the series. Okay, so you can basically obtain the fitted values just by subtracting the residuals from a time series and just overlay them on the graph. So, okay, it doesn't look to be that bad. Of course, we're not doing anything sophisticated in this case. We're just comparing really the actual data with the fitted values. Of course, if we want to be more punctual and more systematic, we would have to plot the residuals. We would have to look at their autocorrelation properties, and we would have to just double check that our model describes sufficiently well the time series pattern here. Okay. Right. Okay. What if though we have multiple time series? So we no longer collect just a single time series. Okay. So the ARMA models extend again in a very nice way to vector autoregressions or vector ARMA models. So here, a simple case can be the vector autoregressive, which is can also be fitted with the function AR in R. So here you've got basically xt to be not scalar, but just a vector with k elements. And these k elements change over time. So a simple case is the vector autoregression, which is, well, just again the sum, say, or linear combinations of the past values of the series. Okay, so here the A, capital A, are just k by k matrices. And if we just want to think of what's the effect in terms of describing the present value, in terms of the past information, well, more of a graphical summary here. If we just think of the simple case where we've got xt to be alpha xt minus 1, and that's a k by k matrix, xt is going to be a vector of k elements. So I can write it as a vector, which is going to be equal to, well, I'm going to have elements here, alpha 1, 1, alpha 1, 2, alpha 1, k, all the way to alpha k1, alpha kk. And this matrix need not be symmetric, right? Times my multiple time series at time t minus 1, element 1. Yeah. element k. So really, if you want to, delve deeper into, how these dynamics actually link with the present value, well, let's just focus on one component only. So the first component here is going to be basically the inner product of this vector with that vector. So the second one is going to be the dot product of the second row with the same vector, and so on and so forth. So in other words, each univariate time series is written as a linear combination of all the previous time series at the previous day, let's say, if we were recording things in days. So there is dependency now in the present value, for each component here. This component is not only dependent on itself, but it's also dependent on other measurements or on other time series. Okay, so that's a quite intuitive model, and it extends nicely to the autoregressive moving average as well. So we've got the ARMA model, for which we can allow dependency on past white noise events. Again, now these events here are also vectors. And the theory somehow extends, well, I wouldn't say in a straightforward manner. It becomes more subtle. In particular, we need more complicated conditions to ensure, uniqueness and identifiability. But you can sort of avoid this by fitting just vector autoregressive models, which are quite useful and intuitive. So here's another example on fitting ARMA models in, European stock prices. So instead of basically using the actual prices, we're just taking returns. So that's, again, an example or a plot we had initially where we motivated, say, the lecture, where we had, say, the German, Switzerland, French, and London stock exchange. Here, though, showing the returns. So if you remember initially, both these stock indices, all of these stock indices had an upward trend. So it would be quite a silly thing to go and fit a stationary time series there. ARMA models wouldn't be a reasonable model to fit. However, looking at returns only, or log returns, we see that these time series now do have a constant mean, and to some extent we might just then think, well, their statistical properties might not be changing that badly over time. And actually, if you plot the autocorrelation functions and partial autocorrelation functions of these processes, you'll see no structure, which will, to some extent, tell you that, well, a stationary time series might be good, but of course there might be structure in higher order moments, like the variance, that we don't take into account here, but we just go straight and fit a ARMA model or a vector autoregression. So in Bayes-R, that you can use either AR or you can use the package MTS, standing for multiple time series. And if you fit the ARMA, automatic model selection will give you practically zero vector mean, which is not surprising. But it also gives you an order 1 vector autoregression. So you only need one matrix, as in here, to describe the present value of all the series in relation to the past values just the day before. So remember, these are daily prices. Okay, so a quick thing here is, well, we know that the sample size is around 1860. So 1 over the square root of the sample size is about 0.023, and that helps us gauge basically which of these coefficients are statistically significant or not. In fact, it turns out that most of the coefficients that are significant are basically for Fuji, CAC, and SMI. And if you just read that matrix, you see really that all these stock indices react positively to a jump in the Fuji. So all of these coefficients are positive, potentially for CAC as well, with the exception of the Fuji. Actually, they react negatively to a jump in the SMI. So, whereas for the DAX, well, these coefficients actually are not significant. So maybe we might want to say that these indices here are somewhat decoupled from the German market. So you see this idea here of using these time series just to as empirical models to tease out some properties of our data. Right. So I'm now going to cover the most important bit, which I believe for ARMA processes is forecasting. So a few words before we just go straight and try to predict the future. So prediction is dangerous, right? Why? Well, we seek to use observed data to make predictions about as yet unobserved events. And why is this so difficult? Well, there are three things we need to bear in mind. So I'm just going to read them. So we've got unknown unknowns. First one. So there are unforeseeable changes in the underlying processes that could occur. Change points, structural breaks, innovations coming from governmental laws or physics we might not have predicted that could occur in a future time point. These are unknown unknowns, right? We just have no control over them. On the other hand, we do have known unknowns, and basically that means that we forecast using a model or a collection of models that depend on unknown quantities. I mean, the fact that we're estimating those quantities does not mean that we know the quantities exactly, right? So there are still known unknowns there. There are parameters to be estimated. Of course, there are unknown knowns, which means that even if we knew the structure and parameters of the model, there is intrinsic variation. The output is random. It's not a deterministic, it's not chaotic evolution of a sequence there. And of course, just a funny one, there's the only known known, which is people tend to underestimate or maybe neglect, some people, uncertainty. Okay, so let's have a look at the simplest sort of toy example, right? We're not in time series dependent situation. Let's think we have data generated by a sort of straight line regression. Okay, so we want to predict the value, call it x plus for prediction, at a future time n plus h, and we only collected data up to time n. And our data come from this straight line regression, so xt is some coefficient, some intercept beta naught, plus a slope parameter beta 1 times time t minus t bar, plus wt. You might sort of wonder, why do I put the t bar? I mean, I could have changed that t bar there. We could have removed it, and it would have been absorbed in beta naught. I mean, it's just a way of reparameterizing linear regression to make the estimates of beta naught and beta 1 uncorrelated. So time is 1 up to n, and we've got a white noise. Basically, we can have a Gaussian white noise here. We can think of WT driven by Gaussian white noise. And t bar is just the average of time. And it turns out, I mean, it's a simple exercise to show that the least squares estimates are, for the intercept, we've got x bar, whereas for the slope, we've got this expression. So it's a sort of scaled covariance somehow. We've got the sum of xt times t minus t bar divided by the square, well, the sum of the squares or the times, or the deviations of your time from the average. Okay, so the natural predictor, if you like, I mean, if we were to know the model exactly, the natural predictor, let's call it tilde x for h step ahead, would be just, let's plug in our intercept slope, and for our time step, which is h, let's just replace time by n plus h minus t bar, right? So, okay, what about the variance of that predictor? Well, of course, there will be some uncertainty in these parameter estimates here. So the variance, let's call it function v, function of the step ahead forecast, which in this case is taken to be h, is going to be the variance of the average, which we saw it's just sigma squared over n. There's no dependence in the data x here. Plus now the variance of this term. Okay, so simple calculation quickly shows that this term takes this form. So the form is a fraction where in the numerator we've got the square of n plus h minus t bar, and the denominator we've got the sum of the square of t minus t bar. Okay, but now if you just focus on this expression, that's just the variance of your predictor, right? And we are under optimal setting. We know the model exactly. We've got very good estimators here. They are uncorrelated. So what's the variance? How does this variance behave? Okay, well, surely it increases quadratically in this quantity here. Okay, but, well, if you think that, if you fix h, yeah, so if you fix h as being like the day ahead forecast, or 10 days ahead forecast, h equal 10, let's say, it's going to shrink to 0 as n grows to infinity. So the more data we collect, our h step ahead forecast becomes better. How is that the case? Well, if n increases, we can pull n out. It's going to come up as n squared. But here we are summing squares, and these grow as cubes. Therefore, you're going to get a 1 over n term there as well. In the end, you're going to get basically a 0 bracket here for fixed h and increasing n. Okay, so that's good. So if the model is correct, the future observations here, xn plus h, which are going to be given by, the equivalent by the defining equation plus the future disturbance, can give us a sort of closed form expression for the variance of the deviation of the predictor from the true value. Okay, so that's easy to see that that's going to be sigma squared plus the variance, which as the sample size grows, it's just going to come up to be sigma squared. Okay, so the terms in this expression, in expression 5, represent basically the uncertainty due to this intrinsic variability in the system. Our system is random. It's driven by white noise with variance sigma squared, and that basically due to estimating the system, which is the variance v. And actually, on top of that, we must add the variability, the variability due to guessing the system. And in this case, we have added plus 0 variability because we know exactly the system is a linear regression. But in the case where we didn't know that, we would have to add that too. So there are 3, important quantities here when we need to bear in mind when we're forecasting the future. There is intrinsic variability, there is uncertainty due to parameter estimation, and there is uncertainty due to model selection. And that's just a simple straight line regression, right? So imagine, that carrying in a straightforward manner to a time series. So, okay, what is forecasting? Forecasting, predicting the future based on the data collected up to the present. And for the purposes of this, of our lectures here, we assume some sort of fixed model, ARMA, let's say. But often we might want to fit several different models and pull forecasts from all of them. Actually, we might end up in situations where different models fit the data equally well, but give completely different forecasts. So still, we might want to do some model averaging there. Okay, so to do this thing, we need to estimate the parameters of the model. But as we said, even if the model structure is known, had the model structure been known, the estimates wouldn't have been the true parameters that gave rise to the data. So we use the assumed model structure and the estimated parameters together to form our predictions, basically. And again, due to the intrinsic variability, even if the model structure and the parameters are known, there will still be randomness due to this intrinsic variability of the system, of the stochastic system. Okay, let's assume, we know the system and we know the parameters, and let's deal with the one component only of uncertainty in forecasting. Right. So we seek to predict the h step ahead, and I think it's intuitive or useful to think that straight line regression, but now in the time series setting with the effect of autocorrelation inflating the variance, complicating things even more. Okay, so here's a quick lemma for starters. So the conditional expectation, basically, of the h step ahead value of the time series, conditionally on the history up to time n, where we observe the data, actually minimizes the prediction mean square error for that future observation based on the data. So it essentially minimizes this decision rule. Okay, that's quite a very useful result. We can think that this conditional expectation basically will be a nonlinear function of the data. But for the purposes of the lecture and the linear time series we're looking, it suffices just to think that this conditional expectation is just a linear function here of what we observed up to time n. So our h step ahead forecast, we might want to form it as linear combinations of our data up to time n. Okay, supposing we've got a mean 0, we've got under a stationary time series mean 0. What we ideally would like to do is to minimize or to find those coefficients lambda that minimize that prediction mean square error. And we can expect that more weight is going to give to recent history than all the way to the past. And these could also be probability weights. So prediction for ARMA. So I'm going to skim that quickly. So that's, ideally our forecasts need to be functions of the data. But of course, it helps in mathematical sense and terms, it helps to use the causal representation where we write our time series as a function of the white noise events. So here's a theorem. So the best linear predictor, say h step ahead x tilde for xn plus h in a causal ARMA process, is actually, it's related to the coefficients of the causal representation of the time series. So it's a sum from log h to infinity, psi j wn plus h minus j. And reading that out loud, it's psi h wn plus psi h minus 1 wn minus 1 all the way to the past. So there are no future events. So in predicting the future here, we're not using any of the future events w. And that's due to causality. So x tilde can be evaluated from the linear representation, from the causal representation with unrealized innovations, so as if we had 0 future events. Okay, so let's see that theorem in some more detail. So consider the linear predictor. So that's just a function of your data, lambda I xn minus y. And we take a linear combination here. And noting basically that, if x is a causal series, we can write it as an infinite linear combination of the white noise events. Okay, therefore, take that guy here, take your linear predictor, okay, and replace your x by its causal representation. So we've got a sum of weighted, say, infinite order linear combinations there. The key thing here to see is that, well, fix I to be 0. You're going to have the coefficient lambda 0. And then you're going to be weighting all the past white noise events. So I0, so you're going to have n minus j. So you're going to start from n minus 1, n minus 2, and so on. Actually, if you expand the brackets here, the key thing to notice is that this has also a linear form in the w's, where we can just postulate that there exists some unique lambdas here for which that is exactly equal to that expression. So our linear predictor now, with the use of the causal representation, is written here as a combination of the white noise events. And for the prediction mean square error, well, take your actual value minus its forecast, square it. Well, it will come up to be exactly equal to the intrinsic variability sigma squared, plus, say, the first h of these coefficients squared, plus now the square deviations of your psi, the coefficients in the causal representation, minus the coefficients we postulated there. So the key thing to see here is that this quantity is going to be minimized basically when, well, that's positive, and that's also positive. So basically it's minimized when exactly, when psi I is exactly equal to lambda I minus h. So we might take lambda I to be psi I plus h, leading to minimum prediction mean square error. And that's good news, right? The prediction, therefore, we know exactly what lambda i's are, so we can shove them in and basically end up with the result of the theorem. So computations, of course, this causal representation helps in terms of the maths, but what we really want to do is have, say, expressing our forecasts as functions of the data. So how do we compute them in practice? So in practice, we really compute them using the defining equation of the ARMA model. So we start by the autoregressive operator times the forecasted value being equal to the moving average operator times the residual at lag h. So here the residuals and the fitted values or predictions are obtained recursively. So basically, okay, so the residuals are just the actual minus the fitted. So we've got these two expressions here for both the residuals and the forecasts. So for forecasts, well, if t plus h is within our sample, well, it's actually the actual value, right? It's not even a forecast. Whereas for h being larger than 1 and t equal to n, let's say, then the forecast is just given by the defining equation of the ARMA. So we just write this in longhand here. And noting that we obtain the residuals just by taking the actual values minus the fitted ones. So here's a quick example which shows that the 8 step ahead predictions for a causal ARMA 1-1 process, which is given by this equation, are basically the next day ahead and the h days ahead are of this sort. And for convenience, we're also given, say, the coefficient psi in the causal representation. So how can we obtain the forecast? So we've got an ARMA 1-1. So I'm just going to quickly go through over that, which is xt equals alpha xt minus 1 plus wt plus theta wt minus 1. So the forecast, the day ahead forecast, t plus 1, is going to be alpha xt plus wt plus 1 plus theta wt. And that's just the next day ahead. Of course, at time t, this is equal to the actual. So we've got alpha xt. And, well, I have no idea what the future white noise event is going to be. So that's set to 0 plus theta wt. So we see we might have to evaluate or calculate a residual there. Whereas for the 2 day ahead forecast, we've got alpha xt plus 1. Well, here I'm assuming basically that t equals n, right? So we've got x tilde x t plus 2 equals alpha tilde x t plus 1 plus w t plus 2 plus theta w t plus 1. So these are both these are future white noise events, so they dump out. And I'm left with alpha tilde xt plus 1, which is equal to alpha times alpha xt here plus theta wt. So to obtain the forecast fully, I really need access to the residual wt, and that also has needs to be computed recursively. So for the residuals, okay, so we've got w t being, say, the autoregressive operator at the forecast minus, say, theta here, w t minus 1. So that's the recursive equation. So we start with w1. That's going to be x1 minus alpha x0. But of course, we haven't observed anything, so we set that to 0. And that's minus theta w0. And that's also the case for w0. We haven't observed that. So we set that to 0 according to these equations. And we end with the residual being exactly equal to the value of a series. We move on to the residual at time 2. That's going to be x2 minus alpha x1 minus, and then we've got theta w1. Therefore, that's x2 minus alpha x1 minus theta. And for getting the residual time 1, well, we just calculated that. That's x1. So the tildes are being dropped just because we are within sample. Therefore, these are observed. But that formulation can be recursively used to, end up with an answer for w tilde n, for which, or wt, sorry, which we need for the day ahead forecast. Just the sort of mechanics or algorithm for, calculating the forecasts, really. So that's pretty much what's on this slide. I'm just going to quickly conclude with 3 comments. First of all, for the best linear predictor with shifted process by a constant mean mu, the best linear predictor is also of the same form, just plus mu. But for ARMA processes, because this psi j converges to 0 exponentially fast, we have really that the forecast after a long a step ahead will basically dump to the mean. So the forecast, if you look at a very long forecast, really what you're going to be answering as your predictions is the mean of the process. So likewise for large h, the prediction error is also going to be, effectively equal to this infinite series, just because this converges exponentially fast to 0. And we can compute the prediction intervals for the future value simply by taking our best linear predictor, just calculated from these recursive calculations there, plus minus the quantile of the appropriate distribution times the mean square error rooted. So just to conclude, so these 2 plots here show the forecast for the sunspots. So again, in our my sort of favorite package here, forecast, is used to forecast basically the fitted AR model with the 9 coefficients, 30 years ahead and 100 years ahead. So these are plotted on left and right hand side separately, respectively, and you sort of see, at least from the left hand side, there's a good match. I mean, there's a sort of reasonable match. It looks like the time series has captured this momentum in the series, so it's going to oscillate. But eventually, as you look longer and longer, time horizons, your forecasts are going to dump to the mean. Okay, so that probably tells you that, well, there are some unmodeled components in that series here that you haven't quite accounted. Still, though, I mean, even a stationary series, you can see what type of forecast it can give. Surely, though, we have just what we've done here with a computer is nothing more, but put here the innovation uncertainty or the disturbance uncertainty. We haven't really said anything about model uncertainty or estimation uncertainty here. So, this previous discussion needs correction, needs more thought. So, a way of say adding the other 2 components, not just the intrinsic disturbance, intrinsic randomness, is through bootstrap simulation, from which we can, create basically pseudo data sets by simulating from the fitted model and then refitting the time series. So just a quick algorithm here. We can start by, for example, simulating x1 star up to xn star from a plausible model of our choice, the ARMA model. And once we simulate these new pseudo data sets, we can fit, say, the same model class to these data sets, but choose, again, the best model by some sort of information criterion like the AIC. So this best fitted model to the pseudo data set is used to obtain a forecast for each of these data sets. And all these replicates are combined to assess the uncertainty of the original prediction. But of course, to do that in practice, you would require some automatic, model choice. It cannot be. You cannot start simulating millions of new data sets and, manually selecting your best model. So I'm going to stop here. that's pretty much part one, and I'm going to hand over to Chris, which is going to be describing the more advanced time series methods. Thank you.